Hello everyone, I'm going to speak about life evolution on Earth, of course, and the importance of fossils as examples illustrating evolution. So to ask directly to the title, is a fossil a witness of evolution? The reply is directly yes, of course, and we will see why, and we will see how life is going on Earth, and what was the past before us, and what is important in terms of paleontology. So I like to start with this almost fossilized object, which is one of the first step of the humankind on the moon, because it's going indeed to be fossilized, as it's the case of other kinds of fossils. This one is from the Jurassic, and it belongs to a theropod, dinosaurs. So dinosaurs were important reptiles, and within the group of dinosaurs you have different species which evolved, including in the present today, birds actually are dinosaurs, feather dinosaurs, but they are dinosaurs according to our classification, according to the phylogeny actually. And we know dinosaurs from the past thanks to different kinds of fossils. Fossils is a large group of objects we are studying as paleontologists, and here you can see one of the first kind, or one of the first type of fossil, which is called Anecho Fossil, which means a footprint or a track. So we don't have the skeleton, we don't have the direct object, but we have a kind of imprint, a natural imprint, which yield important data concerning the dinosaurs itself. It's not leading anatomy, morphology, because there is no, again, bone, there is no teeth, which are also important in terms of remains to study as paleontologists. But these kind of footprints, they yield important information concerning the locomotion, for example, the size of the animal, and so on, the behavior. We even have some footprints in the Cretaceous or in the Jurassic, showing that the animal was walking, then it stopped, and then it turned. So the sense of the footprints turned back, and we don't know why. It's like a snapshot of a behavior a million years ago, and this is like the clues of the detective who needs to make his or her inquiry to give as many data as possible. So footprints are studied in different ways, of course. Here you can see a photogrammetry. We are using precise different kinds of photo to have a very detailed view of the relief of the object, and every footprint is recorded now like that, thanks to this methodology, which allows to study and to analyze precisely the differences between the footprints. Because as you know, if you are wearing different kinds of shoes, you will stay the same, but you will leave different traces behind you. So it's exactly the same. The footprints itself depends on the substrate, so the matter on which the dinosaurs or others extinct species were walking, or on which they were moving. And it depends on your size, it depends on your dermal cover behind the feet, and so on. So we need to analyze precisely all the differences, all the distributions of the variations of these footprints to have a better and a more precise identification as possible. So concerning the bones, here we have concerning the T-Rex, which is a kind of big star in the vertebrate paleontology. We have many fossils from North America, even if we have another species from Mongolia, which is Tyrannosaurus batahar. Batahar means the king in Mongolian language. So it's very close to the T-Rex, but it's not the T-Rex itself. So most of the I would say, Tyrannosaurus skeletons are from the Cretaceous of North America. And you have here behind me, I will try to stay alive, you have a very nice skeleton which is reconstructed in 3D thanks to the 3D itself preservation of every bone. So from this specimen to this reconstitution, this Hollywood reconstitution extracted from the Jurassic world, you have a wide range of possibilities, of course, because reconstruction is involving an artistic touch, because we don't know all concerning the T-Rex. For example, we have skeletons, we have some footprints, we have some imprints of the body, so we have the impression of some scales, but we don't have the color, we don't have the texture, we don't have the skin on the whole body itself. So this, what you see behind me, is just a reconstruction. It depends on the way we are understanding the organisms, and maybe it will be wrong in 1 decade or less, depending on the new discoveries we will make in the future. So a reconstitution of extinct life actually depends on the way we are understanding the species. For example, if you take another dinosaur species like Iguanodon, in the last century, we were thinking that the Iguanodon was a kind of very fat and very slow quadrupedal reptile with a horn at the level of the nose. But thanks to further discoveries, we know now that the Iguanodon is an almost bipedal dinosaur, very rapid, very relatively light, and the horn, we were thinking it belongs to the nasal bone, is actually a kind of phalanx terminating the first digit. So we completely rethought the reconstruction of the Iguanodon from Belgium, actually. So what is interesting is from the fossils you have the field of paleontology, which is studying fossils themselves, but you have also this kind of artistic touch which lead to many novels, many comics, including this ones from Michael Crichton, the Jurassic Park, of course, which is itself not so far from the Conan Doyle's novel called The Lost World, because in both cases you can see dinosaurs alive. So it's possible today, when observing birds, when you are doing birds watching, you are in one way observing living dinosaurs, because we will see that birds today are feathered dinosaurs. But the trick of Michael Crichton is very clever, actually, because he used fossils to allow the characters to observe the dinosaurs alive, thanks to this blood remain preserved in a mosquito itself, preserved in a fossilized plant resin called amber, which is existing, of course. It's very important for us because it's what we are calling exceptional preservation cases, because it's fixing the organisms. Actually, the resin is floating along the trunk, and by floating, it's sticking life, which is living around the trunk, in the trees, and so on. So we have many insects preserved in ambers. We have even some feathers of protobirds or dinosaurs. We have lizards. We have all ecological elements very well preserved, and they are very old. They are minimum 60 million years. If, of course, there are some amber which are younger, some other ambers which are older, but here you can see a mosquito which is fossilized in a amber. So fossilization is a very important process because the way you are going to be fossilized is directing actually the way how one will study you in the future. So concerning another good type of fossilization, here you have the mammoth, which is preserved thanks to the permafrost in Siberia, for example. The soil of Siberia is frozen, and the freezing process preserves organic matter. And this is another case of exceptional preservation for us, because if you have organic matter, then you have direct access of what usually we could have, because a fossil is a permineralized remain of generally the most important part of your organism, the harder part of your organism, which means the teeth, and the skeleton if you are a vertebrate. If you are an insect, you have more chances to preserve your exoskeleton, which is made of chitin. If you are a crustacean, a crab or a lobster, for example, you will have your exoskeleton as well, which is going to be preserved, but it will contain calcium and this chitin, which is a very solid, very hard protein, which is preserving with time. So generally, we don't have feathers, we don't have all what we call the phaner, which is the dermal cover of the organism. In the case of mammoth, what's interesting is that we are looking for fresh DNA to extract from a sexual cell of the mammoth and to re-put or reboot in one way in a living species of elephant of today. So this is technically, let's say, it's possible thanks to the artificial insemination process, which is relatively well masterized, but the trick is to discover a fresh sexual cell of the mammoth, and for the moment it's not the case. So when you are reading newspapers or articles about the resurrection of the mammoth, it's most of the case a mediatic scoop, which is not often based on scientific data, let's say. But what is important for us in case of the DNA, or the fossil DNA, is what we call the Paleogenetician Studies. And paleogenetics is a complete field of studies within the paleontology. And we are indeed using fossilized DNA not to extinct species or to rebirth extinct species, but to better understand them by molecular phylogeny. The trick of molecular phylogeny behind me is that we are comparing DNA of recent elephants with part of the DNA we have from different species of the mammoth, and we realize that first, the mammoth is not the direct ancestor of the modern elephants, it's just a cousin. And this is what we are doing actually based on the whole skeleton of the mammoth. When we are studying phylogeny, we put all the species at the same level, and the game, if I could say, is to make the links, to analyze the relations between the organisms, which are cousins relations. They are not directly related from an ancestor to a living species. The fossilization process is very important, and it occurs in different steps. First, you have the living organisms. This is the first step, which is living, which is reproducing, and so on, eating. And one day it's going to die. So the cadaver must be relatively quickly covered by sediments and by water to stop the oxidation process, because the DNA doesn't like the oxidation process, as well as most of the tissues. And then when it's almost completely covered, then with time, and depending on the physical, chemical conditions of the soils, the mineral matter of the soil is entering within the structure of the skeleton, and the organic matter of the skeleton is diffusing within the soil. So this is why we are speaking about a permineralization process, which is actually a kind of petrification. It's the classical way to be fossilized. But if you are fossilized, again, it doesn't mean that you will be studied by paleontologist or someone else. There is a parameter, there is a chance parameter which is important in terms of discovery, because first we need to have access to different layers. The layers are important because they are strata, sedimentary rocks, which contain or not fossils. So when we are prospecting, actually, we are working on the surface of which we know the age, thanks to previous geological works. We have geological maps. We open the maps. I'm working on what happened before dinosaurs, so different geological periods called Permian or Triassic, in between the Paleozoic and the Mesozoic. So when I'm opening the geological map of the world, we will see one. I'm focusing my field expedition in the regions on which the sediments has exactly the period of time I'm interested on. So this is the first step. The second step is then we are working on this surface. We prefer deserts than forest regions, not because we don't like trees, but we prefer to have direct outcrops, actually uncover outcrops to have a better vision of the sediments on surface. And this evolution of life is very long according to our human scale. Our time unit is the year. The maximum, let's say, time span is around 1 century as human being. In terms of paleontology, on geology, of course, the time unit is the million of years. So it's less than the billion of years for the astrophysicians, for example. It's often represented as a kind of spiral, the spiral of the time of the Earth. And what is interesting is to see that there is a relatively quick turnover because we calculated the older age of the fossils for one species, for one well-known species. We have the oldest fossil and the younger fossil. So we know that in average, it's a global average time period, but if you are an invertebrate, which means an insect, an arthropod, a worm, and so on, you have, as species, of course, not as individual, you have a lifespan of 10 millions of years. If you are a vertebrate, this is our case, the time span is in average just 1 million of years. So they are very global statistics. But what is interesting is that life appears finally relatively quickly because the Earth is around 4.5 billions of years. Early life is around 3 point something, if not 4 billions. So in, I would say, 500 million years, you have already life which appear on Earth. And taking that into account and thinking about the rapid turnover, you can relatively easily, let's say, imagine that life could appear elsewhere in a relatively not so old planet, depending, of course, of the of the conditions. And but if there is life outside Earth, we have more chances that this life is fossilized, because it would be, let's say, anthropocentric to say that life is living at the same time than us. So taking into account the Earth history, we have more chances to find possible life forms as fossils outside the Earth system. But for the moment, we don't know. We know on Earth that life is very complex, evolves very quickly, and it depends on the system Earth itself, which is made of tectonic plates. And tectonic plates are also very important in terms of life evolution on Earth. Here you can see a map of the world today with different spots, yellow spots. One spot is a movement, a seism. And the repartition of the spots corresponds to the limit of the tectonic plates. So you can see the African tectonic plate very easily, which contains Africa itself as a continent, but also part of the southern Atlantic Ocean, part of the Indian Ocean, and so on. So this is moving, and everything is moving. The speed of the plate is not sensible for us, because the movement is around is between 3, let's say, and 6 centimeters per year. So it's, for us, it's nothing. You can stay at the edge of a tectonic plate. You will never see the plate moving, except in case of seismic problems, let's say. But this is to say that life is evolving with the plates, and there are cycles, because in the past all the continents, all the plates were gathered in what we call Pangea. But before Pangea, we have another configuration of the tectonic plates, and this is what we call actually the Wilson cycle. You have different movements in the crust, at the level of the crust on Earth, different movement which is relative to the opening. The tectonic zip is, let's say, creating oceans, but when two plates are meeting each other, they are forming a mountain chain. So it depends on the configuration. And here you will see a very short video summarizing the movement of the plates themselves. There is a small count, bottom right of the picture, with the million years turning very, very quickly. So you can see that before Pangea, the plates themselves were moving. Pangea is not the cradle of life, because before the tectonic plates were, let's say, plain. So if you want to work on dinosaurs, for example, today, you take a geological map of the world, and you will detect the region of the world on which you have interesting sediments, potential discoveries dated from the Triassic, Jurassic, Cretaceous, so between 250 million years to 66 million years, what we call the Mesozoic Era, because this is during this era that dinosaurs evolve. And you are planning field expeditions. So if you are working on what happened before dinosaurs, you will zoom on different parts of the world, like in Africa, for example. Here you can see the geological map of Niger, which is let's say in the center of, or near the center of Africa. It's interesting for us because it's almost completely covered by the Sahara, and thanks to the previous geological works, we know that the sand is coming from different plateaux of cratons of different ages, and we worked with colleagues from North America, South Africa, and Niger, of course. We worked there to look for and to find more amphibians and reptiles of Permian age, so animals, vertebrates, tetrapods of around 260 millions of years. This is a photo of our camp because we are walking in, let's say, relatively isolated regions of the world. We are using the dunes to climb on and to detect what we call the reg. The reg is the typical pebble desert, and there is the erg, which is a sandy desert. So we prefer to directly watch and observe the reg surface, of course, because this is the surface of the sedimentological layers. So this is a nice photo of the dune here. Then you have another photo of our camp at the end of the day. This is the surface of what we call the Moradi formation. Moradi is the name of a Tuareg village not so far from this region of Sahara, on which you can see apparently pebbles on the foreground of this photo, but if you look closer, they are not pebbles, they are directly fossils. They are remains of bones, and I like the comparison between the Sahara region here on the left and the Mars surface on the right of the photo. Here you can see a nice photo of Roger, a geologist colleague from South Africa, brushing and cleaning a very nice vertebral column, which is eroded by the sand winds, which are almost not permanent but very frequent in this part of the desert. So you need first a chance to detect very small, or not small actually, but the first remains, and you need a good chance to detect that at the right time. If you are coming too late, the sand completely destroyed and turned all the skeleton into dust. If you come too early, you will see nothing because the surface is not enough eroded to deliver the vision of the fossil on the ground. So there is a temporal window which is necessary to discover interesting fossils. So how we proceed now on the field, when we find a fossil like that, which is a very nice vertebral column, we dig a small tranchée, we dig a kind of hole all around the structure we are seeing. We test, of course, we brush and we clean everything to see if there are or not connections between the bones, but once there is no more connection, then we dig a small tranchée all around the structure, and we put plaster. We put first journal paper to protect the fossil, then plaster. We make a kind of cocoon to transport the fossil to the closest laboratory, paleontological laboratory, which is in this case Paris. And then we are asking to the travel companies to have this kind of cocoon of plaster. They cannot see what there is inside, so they have to trust us that this is not a bomb, this is a fossil, and we are studying proto-dinosaurs for science and to better know life evolution and so on. So there is a long process of preparation, of prospection, and I would say of diplomacy to allow the data to be really exploited in the laboratory. And when it's coming in a paleontological laboratory, the first step, we don't take the skeletons like that and we don't exhibit them in the museum. There are many different stages in between. The first and very important step is the preparation. We need to clean everything to have access directly to the bone, possibly in 3D. So there is a long period of time of mechanical preparation, sometimes chemical preparation depending on the composition of the rock, composition of the sediment. If it contains some calcareous, some carbonates, then we are using different types of acid. Of course, we are doing some tests before to don't have bad surprises, but this is the way how we are working. In the case of this kind of rocks, they are mostly sandstones, so based on silicates, we can't use chemical preparation, or we are mixing, but the mechanical preparation is finally very important. The colleagues are using a sand jet machine, which is by percussion or by erosion is cleaning the sedimentary matrix all around the fossil. So this is the result. We have a nice view of Gérald, the colleague, which is a preparator in paleontology. This is a real job. And this is a very important job because this is thanks to Gérald or other preparators that we have access to our primary data. And then we are comparing the bones themselves, we are drawing them, we are describing in different views, like anatomists. We are, after all, anatomists, and we are doing comparative anatomy. When we find something which is different, we need to be sure to have compared this bone with all the bones from all the museums of the world to be sure it's different or not. If it's not different, maybe this bone is giving new data on the anatomy of the locomotion because it's a limb bone, for example. But if it's a new thing, then we need to be sure. And if it's not related to anything already known, we are, let's say, obliged to create a new species, waiting for a reply in Nature or Science, depending on the journal. It doesn't matter actually, but this is how we proceed actually. We based a new species description on a list of new characters. We are calling that a diagnosis. We test the new character or not with phylogeny by putting all the characters of the morphological characters in a data matrix with a long list of species. We call that the taxa, and a long list of characters, and we are using parsimony softwares to link the species and then to test the relationships on the new or not character of what we are finding. So here you can see a nice anatomical plate, because this is the basis of the publication. We put the object, the skull, or what we find, in different views: lateral view, dorsal view, ventral view. We are describing as surgeons, actually, anatomically speaking, what we are observing, and we are trying to detect new characters, new anatomical characters. So this is here, this is an anatomical plate of a reptile which lived on Pangaea before dinosaurs' time. This is a Pareiasaurian. It was based on the type of the teeth. It was an herbivorous of good size. It was the size of a cow, let's say, 2 meters, I would say, 2 or 3 meters, depending on the genus and the species. And this gives important information of the fauna of the past, before, during, or after the dinosaurs. It doesn't matter actually, but this is thanks to these elements that we are understanding the different ecosystems on Pangaea, on after, and we are completing the data with what we call histological data. Here you can see a histological section. We are cutting when we have several specimens of the same type or thanks to a CT scan now, which is a non-destructive methodology, we are scanning the inner part of the fossil, and we can see a lot of things actually. We can see if the animal was aquatic, was amphibious, was terrestrial. We can detect sometimes at the cortical level, at around the surface of the bone, depending on the bone, of course. But sometimes we can see lines of arrested growth, exactly like the trunks we are cutting. We can count the number of lines to have an idea about the age of the tree when we cut it. With this kind of fossil, it's almost the same. We have lines of arrested growth, which indicates not necessarily the age of the individual when it died, but at least the rhythm of its own development. So we have data on the morphology, on the anatomy, on the diet based on the tooth morphology. We have data on the ontogeny, which means the development thanks to what we call skeletochronology or bone histology. And here we propose, after all these processes, a reconstruction. We put all the anatomical plate, and we put first an osteological reconstruction of this Paleosaurian, and then we are working with what we call paleo artists. They are artists not from the Paleozoic, but artists specialized in paleontological reconstitutions. They are very often naturalist artists, bird watchers, or herpetologists, amateur herpetologists, and so on, and they help us to add the different layers in 3D or in 2D. After the bones, we add the ligaments, the attach from the bone to the muscles. Then from the ligaments, we add another 3D or 2D layer of the muscles themselves. And then from that, you have the silhouette of the animal. And then we add the dermal layer. The last layer is the dermic one. And the dermic one, if you don't have data, you will use what you know from the most closest species based on your phylogeny, which is preserving the dermal layer by osteoderms or some feathers eventually, or this is how we are working. We are filling the gap even at the level of the osteology, because a complete skeleton, you can see that, yes, in Jurassic Park or Jurassic World, but not in the reality. We have often partial skeletons, even sometimes partial bones, but from that you have to reconstruct based on what you know from the morphology itself, but you are filling the gap from according to the closest species. So this is a nice 3D reconstruction here of the Paleosaurian, and actually we are working as this is to explain you how we are working. This is like a comics from left to the right. You have the 3D scan of the skull, then we add layers of the eyes, balls, the tongue, the muscles of the jaw, and step by step we are reconstructing the robot portrait. I don't know exactly the word in English, but let's say the profile, like profilers, the profile of the beast. So step by step we are working with these kinds of artists, which are very helpful because they give, let's say, life to our very chirurgical way of thinking, because we are, let's say, formatted to publish anatomical plates in certain types of articles and so on. So it's very interesting to work like that with them. So we are even using some interesting instrumentations like drones sometimes. Here you have a photo of a very small but nice city in southern France, in the Var region, called Gonfaron. And Gonfaron is interesting for us because this is one point or one spot in France where you can find Permian sediments, so which means rocks which were sediments of around 280 million years old. And in these sediments, we found interesting fossil amphibians, but the problem is this is above the nice city of Gonfaron at the level of a cliff. So we found a small bones remains, bones pieces which rolled in the slope at the bottom of the cliff. And then when we reach the bottom of the cliff, we observe, of course, the different layers, what we call stratigraphy. We made a stratigraphical profile, but we didn't reach the whole section, of course, because it's vertical, and then we use drones to have a vertical vision of what happened in terms of sedimentology and stratigraphy. And it's very helpful. There is here a photo of the colleagues working directly on the layer which yield fossils, but here you have nice photos of the drone which will help also to try to follow the layer, because we have almost horizontal layers in this region, and we can follow horizontally the extension, the lateral extension of this kind of river sediments, a rock flow which eroded the surface of the landscape at that time, with possible cadavers in the soil again of that time. So here you can see the photo of the cliff, and here you can see a distant photo of the colleagues working at the very precise level. This is what we call a bone bed. It's a bed of rock full of disarticulated bone remains. So this is like a giant 3D puzzle. We need to identify exactly what kind of bone we have. Is it a partial femur? Is it a partial jaw? Is it a partial humerus? And so on. Of which kind, of which type? Reptile, amphibians, and so on. And then we have to complete the puzzle. So it's a very long process before, of course, to have this final step. Speaking again about the T-Rex. So now you have, I hope, a better vision of what is the real paleontological work in terms of vertebrate paleontology, at least. We are not taking fossils directly from the field, exhibiting them directly in the museums. There is a long step of different stages. This is a very nice exhibition here on the T-Rex, and the T-Rex is again a kind of star because we have several almost complete skeletons from the US, so it helps a lot to better understand the species first and the individuals, because the more complete skeletons you have, the more data you have on the same species, then you can understand the growth, what we call the ontogeny, because you will find young individuals, you will find old individuals, so you will have a view of which part of the body is growing first or before another part of the body, what we call a growth allometry, which is important in terms of sometimes species evolution. And you will have a vision of what we call intraspecific variation. Sometimes we have males, females, And it's very interesting to see that sometimes there are differences, as we can find differences in primates, in our case, and in different other clades of different groups. So here you have another skeleton in a North American museum. Here you have another one. So there is here an anatomical plate of the T-Rex with some individuals, not all, but some interesting individuals, almost complete skeletons, which are sometimes scanned in 3D. Every bone is scanned, and then we are building the model in 3D, and we are using on studying what we call biomechanics, so the possible angles of each articulation to better understand how the skeleton itself was moving. So of course, based on the shape of the bone, sometimes there is a natural expansion on the bone, what we call an apophysis, and the size and the shape of the apophysis is directly linked with the size and the importance, let's say, of the muscle. So based on only the osteology, you are able to have or to reconstruct the myology, so the muscles envelope. Here you have a reconstruction of the muscles of the T-Rex. Of course, sometimes when we don't have data, it's based on, okay, I already said that it's based on the species which is the closest species within the group, but sometimes it's based on the living species, because sometimes you don't have the choice. In terms of dinosaurs, especially the theropods, the good living models today are birds. So this is one way, let's say, funny to say that the T-Rex has more common DNA with a chicken than with a Diplodocus, because it's another clade, it's another natural group, and birds and theropods are, let's say, linked together. So from this reconstruction, we can put inside, even if it's not fossilized, this is the working hypothesis, we can put inside the intestines, the liver, the blood system, and so on, depending on the thermophysiology. And the thermophysiology is linked with the kind of bone you have. If your bone is of certain type, then you will have a certain thermophysiology, which is cold blood or warm blood system, or in between, let's say. It depends on the species of the dinosaurs. And there is another interesting fossils I didn't speak for the moment, is the Coprolites, which is the fossilized excrement of the animals, even if it's sometimes difficult to know who laid the excrements, fossilized excrements. Copro is excrement and lithos is the stone, so coprolite is the, let's say, technical name of these kinds of fossils. They are important because we are using, like bones actually, we are using CT scans or classical sections to observe what there is inside, and we can reconstruct the ecological or trophic chain of different individuals. So coprolites, bones, teeth, bone structure, of course, footprints. There are many fossils. On plants, of course, plants are going to be fossilized exactly like animals, depending on the hardness of the structure. Usually, the trunks, when you have a trunk structure with lignin inside, you have good chances of fossilization. Sometimes only the leaves are preserved. It depends on the climate. It depends on the environments. It depends on many parameters, of course. But plants is very important in terms of paleontology. This is a proper field called Paleobotany, which yields many important information, like on the climate, like on the different types of the ecosystems you had at different times periods. Here you can see different types of plants, fossils. We have pollens as well, well preserved. So pollens are difficult to study because they are very, very small, microscopic. So you need a long chemical preparation, but it works. Long preparation of the sediments, but in different solutions to extract, to dissolve the mineral or most of the mineral matter from your sediment, and then you have a long work of preparation of the pollen grains or the palynomorph, because sometimes you have spores depending on which group of plants you are studying on, and depending on the period, and they yield important information as well in terms of climatology, climate evolution, and so on. So after all, fossils are important in terms of evolution because you can study, of course, species evolution thanks to living organisms, because they have DNA, they have their own anatomy, they have their own osteology, and so on. So you are able only with living species to build phylogenetical trees, of course. But with the fossils, you will extend the distribution, your vision actually of the trees by completing the different branches. Here, this is an example with the fish and the tetrapods transition. If you are observing today, the closest, let's say, I'm using fish, but it's not a natural group. We used to speak about aquatic vertebrates, but the closest fish based on the tetrapods. Tetrapods are all the amphibians, reptiles, mammals, and birds, of course, around 30,000 species today. The fish which are close to this natural group, clade, is the lungfish, very peculiar fish known in Africa, in Amazonia, and in Australia. They have both breathing systems. They have gills and lungs, and they look like eels. They are very elongated with small fins, but if you are looking the bones of these fins, you will see that they are composed of almost the same bone elements of our arm, of all the forelimbs of the tetrapod. So this is what we call an homology, a structural homology. And fossils are important because they can give more information about the distribution and variations of these homologies. Thanks to the fossils, we know that we fill the gap between the living lungfish and the early tetrapods. For example, we have the coelacanth. You know probably the story of the coelacanth, which was considered as a living fossils. I don't like this term because actually a lot of species today would be living fossils after all, but this is interesting because it's a fish which is known by fossils of the dinosaurs age, and we were thinking that it became extinct at the same time than most of the dinosaurs, so 66 million years ago, with the impact of the meteorite on the volcanism at that time. And during the last century, a fisherman in his net, discover a fresh coelacanth. It was, of course, a big news at that time. We discover living fossils, but when you are observing closer the fresh, let's say, the fresh fish, you will notice some differences between the fossils we have in the paleontological collection and the characters directly observed on the living species. So it's important because you will make the difference between the fossils and the living species. And this is another step. This is another step we are adding to the phylogenetical tree, because now we know that thanks to the fossil, the fish tetrapod transition is well known thanks to different kinds of fossils from China, from North America, from Greenland. You probably know Tiktaalik or Ichthyostega from the Devonian and Greenland. So it was a kind of giant salamander known by different fossils, and it illustrates the diversification of the almost tetrapods at that time on land, actually. So it's very interesting because by analyzing the fossils, you can better know what we call the important transitions during the species evolution. It's working for the aquatic to the land transition, but we have data of the radiation of the species in the aerial mode of life before birds, of course. Today, the flying animals are typically the bats and the birds, and insects, of course. But during the dinosaurs' times, you had pterosaurians, for example, which are flying reptiles, very interesting. It's a complete extinct group, different from the birds, so fossils are important, of course, to study them, to better know them. And it's illustrating the bricolage, actually, the evolution is doing to try to adapt or not to different kinds of ecosystems, aquatic ones, terrestrial ones, aerial ones, and fossils are showing us that actually the species evolution is a never-ending machine of new variations with wings of different types. If you are a pterosaurian, you will have different wings that the birds, they have different wings that insects, and so on. So you have a never-ending machine of variations which are retained or not by natural selection. And even if you have a super good adaptative fitness or genetical fitness, maybe you will meet an impact of a meteor, and you will become extinct. So this is not enough to be in good, let's say, fitness with your environment. There are many stochastics, parameters to take into account to study life evolution as well. And I would like to finish with this funny picture of a paleo artist from Alaska. Data is under your feet. So this is exactly summarizing actually the work of paleontology, because we are walking a lot when we are prospecting, and then when we are finding some first early remains of bone, then we stop, we put a GPS point, we continue our way, let's say, and on the map we have different spots, different GPS spots, with an evaluation of the density of the bone matter, and we decide or not to open an excavation field to extract the skeletons. So that's it. Thank you very much. And some references at the end about dinosaurs tracks, because this is how I started my talk today about dinosaurs tracks. And another book, Earth Before Dinosaurs, I had the chance to write in French, and which was translated already some years ago. Thank you very much.